Welcome back to Principles Engineering. Today we're going to talk about centroids, and this will be an introduction as we move into statics and material science. We talk about why things hold together and how they hold together and distribute forces. Before we get started, be sure you visit the module and download the guided notes. Those guided notes will help you to retain some information and also capture some of the details of this presentation. Let's get rolling talking about centroids. So the idea of a centroid is essentially the average of all points that define the object. Now, if the object is made of a material that's of uniform density, that also happens to be the center of mass. We label this graphically with that little black and white symbol. That symbol represents the centroid of an object. Now, the principle of centroid is that if I have an object of a given mass, it's being accelerated due to gravity. Gravity's pulling it down. If I apply a force at the centroid, the object will stay in a state of equilibrium or balance along that centroid. So in the picture on the left, the finger supporting the weight, dead in the middle of it, and the weight will balance. The picture on the right, you can see that the force supporting it is offset from the centroid or the center of gravity. That will cause the center of gravity to rotate down and attempt to be vertically directly beneath the force. And obviously it would rotate and fall off the person's finger. So what do we use it for in statics? Why do we care about the centroid? And the reason we care about the centroid here is we use this for some theoretical calculations, talking about how forces interact within a member. And a lot of that is derived from the centroid location. We'll see that at the very end of this presentation. If we put an object in a bending moment, what we will see is along the centroid is the plane, the neutral plane, and that's where the element goes from tension to compression. So talking about a centroid principle, you can basically look at an object, in this instance an I-beam, and we look at what's called the cross-sectional view. So in the image to your right, what you see rotating is that I-beam forms a cross-section that looks like an eye, hence the name I-beam. That's what we mean by cross-section. What would it look like if we sawed it and then looked at it on the end? Now the centroid for a symmetrical object, as you probably already know from your life experience, is in the middle of that plane of symmetry. So if we look at a line of symmetry, an example would be a triangle for the first one, you'll see that the centroid's located along the middle of that triangle because this triangle happens to be equal on the right and left sides, or it is symmetric. If we look at a square, we can take the multiple lines of symmetry, and where they intersect is the centroid. So if I draw corner to corner on basically a square, you'll see that my centroid is right smack in the middle, or any rectangle that would also work. Now a circle, we could put the lines anywhere we want. They just rotate around. They always intercept at the circle because that's the definition of a circle, a line with all points equidistant from its center. So the centroid lies along those line intersections in the center of it. We talk about this with the term X bar and Y bar. So when you hear X bar and Y bar, when we're talking about material science, we're referring to the centroid. You've seen these symbols before, particularly X bar in statistics. Different meaning here. But X bar and Y bar basically display the centroid from a datum. And a datum's nothing more than a reference point or a reference plane. It doesn't really matter what we choose, but in this instance, we've chosen the lower left corner. So when we talk about where the centroid is measured from, it's the lower left corner. And if we look in where X bar is, there it is, measuring in X, and Y bar is measuring in Y. Now, I'll note a caution here. When we do some of the software, you'll see these referred to as CY and C sub Z. That's just the way the software is set up. It uses the Z plane instead of the X plane. If we look at a simple square or rectangle, it's really easy to find that symmetry line. It's always in the middle of it. So all we do is take the base divided by 2. That is the X bar location. And we take the height divided by 2. That is the Y bar location. All of these formulas are located in your formula sheet. And there's our centroid. Now, a triangle doesn't necessarily have an axis of symmetry. I showed you one that did in the last presentation. But in this instance, a right triangle does not necessarily have that axis of symmetry, so we have to calculate it. So if we were to look at this triangle, where would be the geometric midpoint of it? The formula for X bar is the base divided by 3, and for Y bar is the height divided by 3, or 1/3 of the way up and over. Now, in this instance, it's kind of important that we're using the correct reference points. We always want to use that right angle intersection point right here as our reference point. And there's our little centroid symbol. So if we look at a semicircle, a little different than that circle, because the circle, the centroid, is always in the middle again. But a half circle or a semicircle, that is located in the line of symmetry right across the middle, left to right in this image. But in terms of the Y bar for this one, it's going to be represented by the formula 4 times the radius divided by 3 pi. So in this instance, if I go 4 times 2 divided by 3 times pi, I end up with 0.849 inches. So all of these complex shapes, we use a formula. And the formula that we use essentially says that X bar is equal to the sum of the individual centroids times their area divided by the total area. And that's for X bar, Y bar, and Z bar. We can do this in 3 dimensions. So let's look at what this means. And really we boil this down into 9 steps to find the centroid of a complex shape. So this complex shape, when we look at it, we can see that it's made up of multiple smaller shapes. So step 1 is divide the shape into smaller, simpler shapes. So if we look at it, I can cut it in half down the middle and get a big rectangle. Shape 2, I can find a small triangle. Shape 3, I can find a square. The next step is to determine a reference axis. Now, most of the time, it doesn't really matter. So as long as you're consistent. So I'm going to tell you for this one, for ease of simplicity, we're going to choose the lower left side. So that's our reference axis. Now we're going to have to find the area of the shapes. So real quick, in your formula sheet, you'll find all of these formulas for shapes. These are basic geometric relationships. If we look at the area of a square or a rectangle, it's the base times the height. Or if it's a square, well, the base equals the height, so it's the side squared. Area of a rectangle, width times the height. Area of a circle, pi r squared. And the area of any triangle is 1/2 base times height. Okay, step 3. We have now got a datum and our individual small shapes. So now let's find the area of each simple shape. So again, area 1 is the rectangle, and it is 3 by 6. Width times height, or 18 inches. Shape 2 is the triangle. That's 1/2 base times height. So that will be 3 inches tall times 1.5 inches, or 4.5 inches, square inches. Then we need to find the area of the square, which is shape number 3. It's 3 by 3, so it's 9 square inches. So we've got our 3 areas that make up our total shape. Now let's find the centroid of each simple shape, and that's pretty easy if you look at it. Like number 1 and number 3, it's obvious. The centroid is going to end up being in the middle of it. So it's going to be right here, in the middle, and run straight up. Right there, in the middle, run straight across. Shape 3, in the middle, vertically and horizontally. Shape 2, we have to apply our formula. So let's do that. So here's my line of symmetry for shape 1. Shape 2, it's 1/3 of the base and 1/3 of the height. So you can see the base is 3 inches across. The height is 3 inches. So I'm going to be 1 inch over and 1 inch up. And last is the small square. That is 3 by 3, so it'll be 1.5 inches over from its edge and 1.5 inches up from its bottom. So now we've got our 3 centroids for our individual shapes. So that was step 4. Step 5. So step 5 is basically determine where these centroids lie from the reference axis in X and Y. So this is pretty straightforward. If we look at shape 1, it lies 1.5 inches over. Let's do all the X's first. Shape 2, it actually lies 1 inch over from the edge of the bottom of the triangle, but that bottom edge is 3 inches over. So it's 3 plus 1 for 4 total inches. And shape 3, similarly, it's going to be 1.5 inches across from the left edge of the small rectangle, but I got to add 3 inches to that. So it ends up being 4.5 inches total. Vertically, same thing, 3 inches up, middle of the rectangle. 4 inches up, it's really 3 inches plus the 1 inch for the centroid of the triangle. And then the small square is 1.5 inches up. So now I found the centroids of all the individual shapes. Step 6 is multiply each simple shape's area by its distance from the centroid to the reference axis. So first, we make a little table like this. We say, hey, what's the area of shape 1? Well, 18 square inches. Where is the X bar for shape 1 from the datum? 1.5 inches. And I multiply those two together, and I get 27 cubic inches. Same thing for shape 2. Shape 2 is 4.5 square inches, and its X bar location from the datum is 4 inches. Multiply those together, and I get 18 cubic inches. And last, we have shape 3, 9 square inches. X bar is 4.5 inches over from the datum for a total of 40.5 inches. All right, let's do it for the Y locations. And you'll notice the areas didn't change, so I just filled those in. But Y for 1 is 3 inches, 54 cubic inches. For shape 2, Y is 4 inches, 18 cubic inches. And for Y sub 3, 1.5 inches up for 13.5 inches. Now I step back to my formula. And remember, my formula on the top was the sum of all of the areas times all of the x bars. So that was the numerator for my formula. So I go through and I do that. Just add those up. 85.5 cubic inches. Do the same for y. 85.5 cubic inches. So sum the products for each simple shape area and their distances from the centroid. Step 7. Okay, step 8 is sum the individual simple shape areas. So I only have to do that once. It's 18 square inches plus 4.5 square inches plus 9 square inches. That's the total area of this shape right there. Total area. Step 9 is to divide the summed product of the areas and distances by the summed total object area. So for my A sub I times X bar sub I got 85.5 cubic inches. For my A sub I times Y sub I got 85.5 cubic inches. So I now divide 85.5 by 31.5. And I get an X bar of 2.71 inches. Do the same thing for Y, for the Y bar of the complex shape, and I get 2.71 inches. And you're going to notice that this thing is symmetric, isn't it? Yeah, sure is. We can draw a line smack down the middle there, and that line of symmetry is left and right on it. So that's the center of this object. Now, if this object was uniform material and uniform thickness, I could support it by putting my finger directly where that centroid lies, 2.7 inches over from the left edge, 2.7 inches up from the bottom, and it's 2.71. And it would balance. Now, there's an alternate way to do this. It's still 9 steps. It's the same thing, only slightly different. So if I look at this problem and I say, hey, I could divide that area into a bunch of small shapes, I can also look at that and say, I can make one big shape and take 1 or 2 small shapes away. So this is the subtractive method. Same equations, almost the same process. The only difference is for areas that we subtract, we call them negative areas. Negative areas. Now I know that's dumb. There's no such thing as a negative area, but we do that for the mathematics in this. So let's look at this shape. What we really see, or what I see when I look at it, is a 6 by 6 square. And it looks like there's a 3 by 3 rectangle cut out of that 6 by 6 square. So first I'm going to start out and determine that reference axis. And I'm going to use the lower left, same one. And square 1 is going to be the 6 by 6. Now I'm going to say, what do I need to remove to get the centroid? That's step 2. And that is that 3 by 3 triangle. So I've got shape 1 and shape 2. So let's calculate the area of each simple shape. So shape 1, width times height. 6 times 6, 36 square inches. Shape 2, 1/2 base times height, but because we're removing it, it's a negative area. So that ends up being 1.5 times 3 inches squared, or 4.5 inches squared. Notice the negative. We're removing the area. Step 4. And this is again for the subtractive method. Determine the centroid locations of shape 1. That's pretty easy because shape 1 was a square, so we know it's in the middle of the square. That's 3 and 3. Shape 2, a little more work, but again, it's 1/3 of the base, 1/3 of the height, but notice it's measured from the right angle side. It's 1/3 from that side, not from the bottom down here. Now determine the distance for each centroid. Our reference plane is the left-hand side and the bottom of the big square. So for the big square, for shape 1, it's 3 inches. For shape 2, it's actually 6 inches minus 1/3 the height, or 1 inch, for 5 inches. We determine the y the same way, 3 inches. The same logic. It's actually 6 inches tall, and we're subtracting 1/3 the base here, which is 1 inch, for 5 inches. So now we've found our centroid locations. We do the same idea. Multiply each simple shape area by its distance from the centroid. Same table. Area 1, 36 square inches. X1 is going to be 3 for 108 cubic inches. Now this is an important idea. For area 2, remember, it's a negative area, minus 4.5 square inches, and it's 5 inches over for a negative 22.5 cubic inches. Do the same thing in Y. Same areas, 3 inches for 108 cubic inches, and 5 inches for minus 22.5 cubic inches. If I add these together, 108 plus 22.5, I now get 85.5 cubic inches. This is the numerator in our formula for a complex shape. So sum the products of each simple shape's area and their distance from the centroid to the reference axis. Step 8, sum the individual areas. Again, negative area because we're subtracting the triangle away. 31.5 square inches. Divide the summed product areas and distances by the summed total object area. And I get the same answer, 2.71 inches. Notice the line of symmetry again. Pretty straightforward. So whether you use the additive 9 steps or the subtractive 9 steps, the process is almost identical. And we're always using this formula. So remember, this top basically just says sum, sigma means sum, of the individual x bars, x bar sub I, times the individual areas, a sub I, divided by the sum of the areas. And this applies in X, Y, and Z. In our class, we're going to do uniform thickness objects, and we're only going to do two-dimensional centroids. Okay, so how does all this come into play? When we look at an element or a structural element, you're going to see these all over the place. So the next time you're in the building, look up. Look up at the ceiling and you'll see these. Look up at any structure, you'll see them. So let's look at some common elements. And the thing that's common to all of these is they all start essentially with a square, don't they? Or a rectangle, rather. And it's a rectangle that I hollow out. It's a rectangle that I cut material away. But they all effectively are the same. So the shapes here are a rectangle, an L, a C, an I, and a box. And that's the picture of them with the material, how they were made to cut material out of that rectangle. Now looking at L shape, we can think of this a couple different ways. We can subdivide it into two different rectangles. So there's one orientation for the two rectangles, and we could calculate the centroid by calculating the individual centroids, the individual areas, and using our formula. Conversely, we could flip the rectangles over. look at a C. You can see that we could make a couple of different rectangles. There's one version. There's the second version. And there's two more ways we can do this. We can do a long line on the bottom and a short one on top, and a long line on the top and a short one on the bottom. So that's how we can make a C out of basic shapes. A box shape, see, we can break it into 4 rectangles. We can arrange them so that they're stacked or they lie between. Or I can alternate and make the two sides the same length but slightly longer. Now, this doesn't really matter however I represent the yellow on the right and the green on the left, or the yellow on the left, the green on the right. It's essentially the same shape. It's just rotated. An I-beam, you can imagine you can do this a couple different ways. I can chop it off and put the eye in the middle. So there I've got 3 rectangles. So when we look at these centroids, we're really looking at how we calculate the strength of a structural member. And when we're calculating the strength of a structural member, we kind of have to, well, we don't kind of, we have to calculate our centroid. If the member is subjected to bending and the stresses remain in the elastic range, in other words, we don't go beyond where we deform the material, then the neutral axis, looking at it from the end, or the neutral plane in 3D, passes through the centroid of the section, the middle of it. So that centroid is always located on the axis of symmetry. For a simple rectangle, the location of centroids at the intersection. So let's look at this particular piece. And here I've got a beam supported, and there's the cross-sectional view of it. It just looks like a rectangle. Now the centroid of this is located right across the middle of it. Now I'm only showing you the centroid in Y because we're going to apply a load to the top of it. So where the centroid is located right here, this is referred to as the neutral plane. That is the neutral plane. And it's the axis of symmetry that the centroid lies on. So there's my centroid. Now when I start to push down on this thing, here's what happens. The top half of the material on top of the neutral plane, that material, the atoms in it, go into compression. They're squeezed together. The bottom half, below the centroid, those atoms go into tension. And you could see this on almost anything. One of the things to talk about is like a loaf of bread, or like a piece of bread. And as I start to bend that, the top squishes together and the bottom rips apart. So it goes under more and more load, the force coming down. So that's the force arrow coming down on the top. Compression is on the top, tension is on the bottom, and the neutral plane lies between the two. So that's why we want to look at how to calculate a centroid. So in this lab, what you're going to do is you're going to mathematically calculate some centroids based upon some problems. Then you're going to experimentally also calculate a couple of different centroids of some fairly odd shapes. Last thing you're going to do is you're going to use some software that'll help you to predict the centroid of different sized shapes based upon their flange. Thanks for watching.